Hi folks, Mr. Long here. We're going to do a screencast, or rather I'm going to do a screencast on what's called implicit derivatives and implicitly defined relations and functions. An example of an implicit function is a circle, and you're going to see why in a second. So what does it mean to be explicit or implicit? I think we know from just from vocabulary, from the way we talk to people. If I wanted to say to someone it's cold outside and say it explicitly, which is a very direct way of saying it, I just look at them and I say, it's cold outside. If I say it implicitly, it means that the meaning is implied. I'm not direct about what I say, and they have to make an inference, right? So they have to infer some meaning. So if I looked at someone and said, you know, you really should wear your winter coat today, there's an implied meaning there that, in fact, it is cold outside. Okay, so direct is explicit, indirect or implied is implicit. Well, the same thing is true about functions in math. So if we have this straight line right here, y equals 3x plus 2, and we want to define that function explicitly, it means we have y isolated. And it's very easy to get the derivative of that, right? So if y equals 3x plus 2, the tangent slope of that is always 3. Whoops, I better get a pen. Is always 3. All right, so over here, I've got what this is called an implicitly defined relation. Okay, so you can see y is not by itself. So interpreting this is a little bit more difficult, right? It's hard, everything's all mixed in together, the x's and the y's on one side of the equation. So I can't be 100% sure what's going on here. So what I do in this case, what I can do, and you can't do this in all cases for sure, I'm going to get y by itself. So I notice that 6, 2, and 4 are all even numbers, so I'm going to divide everything by 2. And that's going to give me 3x minus y plus 2 equals 0. And then I'm going to get y on one side. So I'm going to add y to both sides, and I'm going to end up with 3x plus 2 equals y. Well, what do you know? It is the exact same line. Okay, 3x plus 2 and 3x plus 2. They did not look the same, but they're equivalent representations, right? This goes all the way back to grade 9, standard form of the line. So when I differentiate this in this form, I have to differentiate that y, okay, and it's defined implicitly. So when I see a y, I should be writing, I mean, really what I should be writing is dy by dx. But the shortcut for that, of course, is y prime. So the derivative of 6x is 6. The derivative of y is y prime, so minus 2y prime. The derivative of 4 is 0. The derivative of 0 is 0. So that equals 0. And again, here, what do I do if I want to get y prime by itself? So again, I should have written here, like that theoretically, I should be writing, or not theoretically, math notation-wise, it really doesn't matter, but dy by dx is much more formal. Okay, so now I'm going to divide everything by 2. And so I'm going to have 3 minus y prime equals 0. Then I'm going to add y prime to both sides, and 3 equals y prime. So what do you notice? We get the exact same results. Okay, there's a lot more work to doing it implicitly. So when we have an implicit relationship and we see that y only appears once, I can always just isolate for y and then carry out my derivative. On the other hand, the reality is that it's often easier to do it implicitly. Okay, and most functions, I don't know if you remember back, but most non-functions are defined implicitly, right? Because you have y squared, so you can generate a plus and a minus. That's why it fails the vertical line test, because you get a plus and a minus at 1x values, plus and minus y values at 1x value. Okay, so that's an introduction to implicit and explicit. So just what we're going to do now is take a look at, this is the equation x equals y squared, and we're going to look at tangents at x equals 4. And of course, we'll get 2 tangents here because there's 2 branches to the curve. But first things first, this is to me the hardest part to understand. Now, we've done things like this already, right? If y equals f at x cubed, then what does y prime equal? Well, I have to use the chain rule. So the outside derivative is going to be 3 f at x squared multiplied by the inside derivative, and the inside derivative is f prime of x. Okay, so that's what that equals. That's the derivative. Now, if we write it the other way, which we totally can, I could just switch the order and say f at x, define f at x as y cubed. I mean, I could do that, right? It's no different. In fact, it's the same relationship, right? So the hard thing is that we have to remember we have to do the chain rule with this, because this is the chain rule, right? That's my inside function, and the outside function is, I'll maybe show it there. This is my outside function, and my inside function is this, okay? So in this case, what we have to do is we have to consider this to be f at x equals y cubed, with the inside function being here and the outside function being here. Okay, that's the outside function. So, so now what I have to do is I have to do the chain rule again. So when I look at this, I have to do the chain rule. So it's just like f at x. So I'd have to write 3y squared, that's the outside derivative, right? And then I have to multiply by the inside derivative. Well, what's the inside derivative? Just y prime. The derivative of y is y prime. Okay, so I have to see it that way. So the derivative of y cubed is 3y squared multiplied by y prime. Okay, it's the chain rule. If you notice, it's the exact same as this. Okay, so let's go back over to this. So I've got this equation here, x equals y squared, and I want to figure out what the tangent slope is at x equals 4. So if that's my original relationship, I can't call it an original function because it's not a function, but what I'm going to do is I'm going to differentiate both sides. D by dx of x is d by dx of y squared. Okay, so remember that I'm differentiating with respect to x. Okay, it's I'm getting slope dy over dx. So the derivative of d by dx of x is 1, but this, remember, I have to use the chain rule. So the derivative of this is, the outside derivative is 2y to the 1 multiplied by, ooh, that looks like a prime, doesn't it? So I'm actually going to get rid of that. It's going to be 2y multiplied by the inside derivative, which is just y prime. Okay, so 2y, y prime. And I know that's the hard part. So now, what does y prime equal? Well, look at this. Y prime, I'm going to divide both sides by 2y. Y prime actually equals 1 over 2y. So what's interesting about this is all I have to do is plug in the y values. So if I want to get the slope right here, the y value is 2. So y prime equals 1 over 2 times y. Y is worth 2. So that's 1/4. Now if I want to get the slope right here, so notice we're having slope being defined in terms of y now, not just x. That's what's really interesting about this. And this is going to allow us, by the way, to solve differential equations. It's the reverse of this implicit differentiation, is solving because we're making a differential equation actually. So y prime here is 1 over 2y, and what's y worth right here? It's worth -2. So it's -1/4, okay? So we can get tangent slopes now of non-functions, and we couldn't do that before. Okay, so now we're going to do some practice of some derivatives. Okay, so this first thing is a circle, and again I need to do d by dx x squared plus d by dx y squared equals d by dx of 0. Now after a while you're not going to do this, right? Just initially. So the derivative of that is just 2x. I don't have to do the chain rule because I'm already differentiating with respect to x. Now I'm going to do the chain rule. So remember, that's the inside function, y, and the outside function is squared. So it's going to be 2y to the 1 multiplied by y prime, and that equals 0. Okay, now I have to isolate for y prime. And remember, that's just dy by dx. Every time you see y prime, it's the same as dy by dx. So I'm going to have to subtract 2x on both sides. And then what am I going to get? Well, I'm going to get 2y, y prime equals -2x. And then I have to divide by 2y. So y prime will then equal -2x over positive 2y, which equals, the 2's divide out, so it's going to become -x over y. And that's the slope of any circle, -x over y. Okay, again, pause, rewind, go through this again. You should probably be writing these down. This next one. So now, if we notice, I've got x times y to the fourth. Okay, that's, now I've got the product rule, right? The product rule. So for this one, what I'm going to do is leave the 3 outside, and then I'm going to do d by dx of xy to the fourth plus d by dx of y equals d by dx of 12. So if I look at this, what I'm going to do here is I'm going to have to do the product rule. That's a and that's b. So it's going to be 3 and then a prime b. So that's going to be the derivative of a is 1, and then b is y to the fourth plus a b prime, x multiplied by b prime. Well, what is the derivative of y to the fourth? Well, we know it's 4y cubed multiplied by the inside derivative, which is y prime. Okay? Then I'm going to add to that the derivative of y, which is just 1 multiplied by y prime, and that will equal 0. And so what we see here is, this is where things get a little bit tricky. I've got to start doing some factoring, okay, and moving things to different sides. So something I can do here is expand the 3 into the brackets, right? Expand that 3 in, so I'm going to end up with 3y to the fourth plus, and then I'm going to get 4xy cubed y prime plus y prime equals 0. And I'm going to subtract 3y to the fourth off both sides. So I'm going to be left with 4xy, oh, sorry, and then what I want to do is, I might as well do this efficiently. Okay, I might as well do this efficiently. What I need to do now is common factor y prime out of that. Okay, common factor y prime from that. So how will I go about doing that? How will I common factor that? Well, I'm going to do what I'm going to do is this. I'm going to have y prime, and then I'm going to be left with that 4xy cubed, and then I'm factoring y prime out of that plus 1, and that equals negative 3y to the fourth because I subtracted that off both sides. And now I just divide by 4xy cubed plus 1. Okay, and that will isolate y prime, which is dy by dx. So negative 3y to the fourth divided by 4xy cubed plus 1. Pretty complex looking derivatives. And remember, that's just the tangent slope. It's still the tangent slope of a curve, okay, but it's a pretty funky looking derivative. Again, rewind, rewatch. The factoring is important. There's a variety of things that you make sure you need to be doing. Oh my God, I made a mistake. What's my mistake, folks? As per usual, I forgot to multiply the 3 into that. So that number there, where I see a 4, should be a 12. So I'll maybe write that in green. So that should be a 12, and that should be a 12, and that should have been a 12. So kudos to you if you saw that before. Again, I always tell you to factor that out, and then I often screw it up when I do it. So I don't know, maybe I shouldn't be doing that. All right, let's move on. Now this next C, I'm not going to do C because I think you're going to be able to do this now that you've seen the factoring. What I do want to show you is a little shortcut that really helps with doing derivatives. So we know when we get something like this, right, that we're going to end up with lots of fractions. So what's something we can do to both sides here to remove fractions? I can cube both sides. By fractions, I mean fractional exponents, because that's 6x plus 1 to the 1/3. But if I cube both sides, look at this. I'm going to get y cubed equals 6x plus 1. And then I differentiate this, and it's going to be 3y squared multiplied by y prime equals 6. Y prime equals 6 over 3y squared, right? Divide both sides by 3y squared. And then there's what y equals. That's what y equals. So instead of, so I'm going to circle in red, y is worth that. Okay, y is worth that. So now what I can do is just replace y. So now it's going to be 6 over 3, and then y is worth the cube root of 6x plus 1, and then I square it. Okay, and I'm done. Okay, so I don't have to work with fractions at all. That's y prime. So that's helpful when you have, like the one, here's one that I would try if I were you. Y equals 1 over, say, the 4th root of 8x squared plus 3. Okay, try that. And I guess the first step would be to go y equals, well, you could do 8x squared plus 3 to the negative 1 over 4, and then raise both sides to the exponent of 4. So you'd end up with y to the 4th equals to the negative 1. And then you just, in that case, you would need the chain rule, but I think you're going to find that it's a little bit easier doing it that way. Okay, so I would try that one. So try that then one the normal way, and then with the chain rule, and then try it with making the exponent, getting rid of all the fractional exponents. Okay, folks, so again, pause, rewind, go over this. There's going to be a part 2 of this where we use it. We go into a little bit more depth on how we can use these derivatives to understand graphs.